also hear me. Okay, good. So then I just start. Yeah.
Please do.
Okay, thanks. Okay, hi everyone. I hope you're enjoying the summer school so far. So my name is Marlene Kretschmer. I work at the University of Reading. I'm doing a postdoc here, and I will give 2 lectures on causality. The first was today. Tomorrow, actually, there is a 2-hour session of the practicals with Elena, and on Thursday, I have the second lecture. So, well, in the previous talks, there have been already some discussions on causality and how to bring or how to use physical reasoning to attribute trends, for instance. And well, we talk a bit more about this, and especially we talk about this a bit more from the statistic or mathematical perspective. But the talk won't be heavy on any equations or anything. So it's really about the concepts. So to start, I like this XKCD comic called "Correlation Does Not Imply Causation," which I guess most of you have heard of the statement. So in the cartoon, 2 people are talking, and one says, "I used to think correlation implied causation, but then I took a statistics class and now I don't." And the other person replies, "Well, it sounds like the class helped." The first person saying, "Well, maybe." And I think this actually, well, I hope you get the joke, but I think it really exemplifies some of the problems, let's say, of the issue when we deal with correlation and causation. Well, we all know the statement that correlation does not imply causation. So, and of course, this shows that we should be careful when we interpret correlations causally, which we know from all these different examples of some funny correlations with the chocolate consumption and Nobel laureates, for instance. But at the same time, I think it also shows that sometimes when we have a causal understanding, for example, in this case, it's pretty obvious that the statistics class was the cause of knowing that correlation does not imply causation. But we're often maybe even too careful, too afraid to make causal conclusions from data, just based on our judgment when it comes to scientific data analysis. So, and this is basically what this talk is about. So in essence, this lecture, or what the aim of this lecture is that I will try to argue how to include causal reasoning in the statistical analysis to actually draw causal conclusions from data. So to move beyond correlations. Well, and very basic structure. So I will briefly motivate the need for a causal concept in climate science, then talk about the mathematical concept briefly of causal inference. And then we actually take some time to go through some concrete examples from climate science in the context of teleconnections. And then I will finish or will dedicate some more time to summarize these different findings, bring them together, and also give an outlook what we deal with this in the second lecture. All right, so let's start. Again, in this well, also given the background of against the background of the previous talks, but also generally, I think we all agree that we need a causal understanding of the world. On the one hand, for decision making, but also in generally for many forms of theory and research. And I'm giving you 4 examples of maybe typical questions posed in climate science or by climate scientists, but this list is obviously not exhaustive at all. But just to give you a hint that causality always is part of research usually. So for example, we ask what is the effect on global mean temperature if greenhouse gas emissions are increasing or further increasing? Will climate change lead to more intense extreme rainfall events in the UK? Or more, well, unrelated to climate change, we might also ask, is El Nino increasing the chance of a drought in South Africa? Or what is the effect of melting Arctic sea ice on European climate? So all these different questions, they have obviously a causal component. So we're not just interested whether 2 things are associated, but we want to predict what will happen or what could happen, but we also want to give explanations. So we also want to address the why. And well, usually, and when science, we can make experiments, we can make randomized trials, for instance. But of course, we just have one Earth system, so we cannot really intervene in the planet. So we cannot compare 2 control groups, one with El Nino events, one without El Nino events. So real-world experiments are usually not possible when we talk about the climate system or the Earth system. But we of course have numerical climate models, so we can make we can use climate model simulations, or we make targeted interventions in climate models to infer causal relations about the climate system. So this is really the idea of making an intervention. So we intervene in the system by just well, increasing one parameter, or taking off sea ice, for example, or increasing greenhouse gas emissions in our climate model, and then we let the model run, and then we can infer the effect. We can see what or we can see what happens or what changes in the model, and then we can attribute this to the parameter we change, so it's to its cause. Well, the obvious downside is, of course, that these inferences about the real world, they really depend on the realism of the climate model. So when we make inferences, we need the model to be actually a good fit for our causal question. That's why we use usually different climate model simulation, or we first evaluate the climate model to see whether it's fit for our purpose. So, but this is, let's say, the usual approach how causality is inferred in climate science, which of course is, aligns with our physical understanding of cause and effect. But again, this also shows that when we just use the observational data of the Earth system, or could be any kind of data, could also be model data, but think of observation data, we are usually bounded to use statistics or data science methods to study causal relationships. However, this is usually limited to take these purely statistical associations, such as correlations. But again, as we have all learned or heard, correlation does not imply causation, but yet we are interested in answering these causal questions. So this kind of sets the scene that of the question I'm trying to address here is that how can we infer causal relationships from observed data or from data without making any actual interventions or experiments with our planet? Well, the answer is causal inference, which is actually a mathematical discipline. So I'm here where there are different scientists or mathematicians who worked on causality, but one of the pioneers, and actually the concept of causality I'm adopting here, is from Julia Pearl. And the book Causality is really the seminal work, kind of summarizing the key findings of this research. And then there, a few years ago, he also published the popular book, The Book of Why, which I can really recommend, which kind of addresses the main ideas and brought also these concepts to a very to a broader audience. In this book, you can also read a very nice chapter on how the concept of causality has long been missing in mathematics, actually for some historic reasons. That some statisticians, they really thought, Fisher, for example, Pearson, they really thought that correlation is all we need, which I think, again, especially we or as physicists maybe, or with a physical background or climate science, we know that we have to, like I already argued, we have to move beyond correlation. Anyway, so in the last years, really the concept, or the last decades, the mathematical idea of causal inference from data has emerged and really created this mathematical discipline of causal inference, which is basically the science to extract causal information from data, again, without doing interventions or experiments. You can, by extracting causal information, there are two main things one can think of. On the one hand, it's about learning causal relationships to see if I have two different variables, for example, greenhouse gas or CO2 and temperature. I want to learn the causal relationship. So basically, what is causing what are maybe the related time lags, etc. And the second point is really to quantify causal relationship, to say how strong a causal effect really is. And in this lecture, I will focus on the second point, so how we can extract or quantify causal relationships from data. What Pearl also described in his, oh, someone is drawing on the slides, I think. Okay, anyway, so what, can you all see these green lines? Where they're not mine.
Yes,
Yeah, we can see.
maybe
whoever's doing that, maybe they could stop.
Well, it doesn't. I think you can still see it. Actually, well, it's a nice feature. I should use it in the next lecture. Anyway, so so what Pearl describes in his book, and also in the book of Why, for example, this is where the drawing is from, is that there is a 3-layer causal hierarchy, also called the ladder of causation, which includes seeing, doing, and imagining. And if you and it really makes sense when we think about causality, also from a mathematical perspective, to differentiate between these three things. So on the lowest level, we have seeing. So it's really just about association. So we can compute observational conditional probabilities, for example, the probability of seeing y given x. So this is basically just correlation. And but again, we cannot make any causal inferences from this. We can just say, how does y look like given some state of x or the other way around. But again, based on this, we don't know whether x causes y or y causes x. But what we're actually interested in is really predicting effects of interventions. Again, the same idea if we run a climate model experiment. And this is what Pearl introduced, is the so-called do operator, which you see in this expression, which is denoting the interventional probability or condition probability. So in this case, we're interested in what happens to y after we do something with x, after we set x to a specific state. So again, the same concept as with running a climate model experiment, but just expressed mathematically. And this is, of course, where cause and effect comes in, because we say something that x causes y if we intervene in x, and when we see a change in y following the intervention. And then there's actually a third level on counterfactual, which goes from this population-sized intervention to the individual level, where we could really answer some questions like, would I still have a headache if I had taken aspirin an hour before, something like this. But in this talk, I will focus here on moving from association to intervention, and leave out the counterfactual. Okay, so to make this distinction clear again between association and intervention, consider this data here. So we have collected data of some process or some variable x and y, and we can see that there is an association, or the association is linear, as we can just judge by eye. So there's a strong correlation of x and y. This means that we could probably also use x to predict y, and we could also use y to predict x, assuming the system is more or less stationary, which again might not be the case with climate change. But anyways, we see the data is correlated. So there's an association. Now talking about this lowest level of the hierarchy. But now we want to predict, again, we want to make causal infer causal relationships or quantify causal relationships just based on the data. So we want to make statements like, what happens if to y if we intervene in x? So what happens if we do x? But answering this is, as you maybe already see, is actually not possible, because the answer to this question, to the effect of an intervention, really depends on the causal relationship of x and y. If x causes y, then we will have an effect on y after we intervene in x. But if y is causing x, then intervening in x, oh, the person drawing is back, then intervening in x will not have any effect on y. And the third option is there's a common driver z, which affects both x and y, which is also possible. We would also see such a correlation between them. But then again, also intervening in x will not have any effect on y. So again, it's not possible to make statements of intervention just if we just look at the data. And I think this in general shows that data usually does not speak for itself, but we need some kind of causal reasoning. To give an example, so if we know what the data represent, so let's say x represents the pressure at some location, and y is the measured pressure by a barometer. So now we have an understanding of the data generating mechanisms, and in this case we can also say what will happen after intervention. So if we intervene in the barometer, for example, move the needle by hand, this will not lead to any changes in the pressure. But if we intervene in X, so if we could have some possibilities to change the pressure, then this will of course also lead to a change in the barometer. Well, making this example again with data. So if our question was, what is the effect on Y if we do X equals 1, for instance, so if we intervene in X, we first need a so-called causal model. So we have to need some kind of idea how the different mechanisms are related. And in this case, we assume that X is a cause of Y. If we think that there is no other maybe common driver involved, but this is really a good causal model of the data we see, then we can actually, or we can sometimes estimate these cause effects just based on the data, so to predict the intervention. In this case, for example, again, we are interested in this interventional distribution of Y after doing X equals 1. And the idea is that also naturally occurring interventions are there in the data. And in this case, there are no other confounding factors involved. So we assume that the intervention probability is the same as the observational condition probability. Then we can, for example, fit a linear regression line to quantify the effect of X on Y. In this case, find it to be our X to be just some random variable and Y to depend on X. And for example, now if we would do X equals 1, so if we would set X to 1, we would estimate Y to be 1.5 plus noise. But again, well, this seems something like we do all the time. The answer is, of course, fundamentally different if we assume that Y is a cause of X. Then we would not assume to see, then the conditional, sorry, if Y is a cause of X, then of course the conditional probability, the interventional condition probability is not the same as the observational condition probability. So what I try to show with this toy example really is that to make sense of data, we need causal knowledge about the data generating mechanisms. So we need to have some understanding how the variables are, or the variables are causally related. The good thing is that in climate science, or generally in science, in scientific data analysis, we usually have such expert knowledge available. So we never stop, we usually don't start at zero, but we bring in our knowledge. So the point here is that we should also make use of it in a kind of formal way, which again is described, or which is described by the mathematical discipline of causal inference. So before I move to actually concrete examples from climate science, I will try to first summarize these different steps of causal inference. And they might seem a bit abstract at the moment, but again, I hope they will become more clear after giving also these concrete examples. And then again, we have the practicals in the second lecture. So the idea is actually very simple. So again, let's assume our scientific question is that we're interested in quantifying the average causal effect of some variable X on Y. For example, X could be El Nino, or maybe Y is drought in South Africa, or could be any other example. Then the difference in causal inference to not just first analyzing data or correlating data is that one starts with actually drawing a plausible causal model of the mechanisms. So in the previous example, we just had X and Y, so just two variables. But often, of course, we assume that there are more variables involved which might play a role. And one key point in causal inferences, or what has been shown, is that it's really efficient or beneficial to set or to describe this causal model or this expert knowledge using so-called causal networks. So it's really just drawing a little diagram or schematic overview, if you like, where the different nodes represent different variables, and an arrow indicates whether one assumes or hypothesis has the hypothesis that there is a causal relationship between these variables. So in this case, we're interested in the effect of X on Y, but we think there are these other variables which play a role for our analysis somehow. Of course, this causal model is not representing the full Earth system or the full truth. It's really just a reduced model of the truth, which kind of captures the essence of the mechanism one tries to quantify. Then in the second step, one collects data to represent these mechanisms. For example, if X was ENSO, then we would pick some kind of El Nino index, for example, Nino 3.4. But of course, this collection of data or this choice of data also involves some subjective choices, just as it's always the case in statistics or in data science. And then it's about bringing this causal model and the data together. So in contrast to just studying the data without any causal assumptions or without explicitly formulating the causal assumptions, we make the assumptions explicit before in the first step. And then we kind of try to extract the causal effect we're looking for from data. So again, in this case, we're interested in the effect on Y after doing X, so this intervention condition probability. We can see, and then based on our network, we can see where this effect, where causal information is flowing based on our assumptions. In this case, we have this one pathway from X to Y, which is mediated by a U. And then we have to control for all the confounding factors, which kind of bias this causal effect, which again is assumed to also occur naturally in observed data. Sorry, I'm confused by these green lines. So we have to control for all the confounding factors to isolate this causal effect we're interested in. And by confounding, it's really in anything that leads to this observational condition probability being different from this interventional conditional probability. Because we can estimate the first one, but we cannot estimate, or we cannot actually make these do experiments. This is more like a thought experiments. So the idea is to express this interventional condition probability without any expressions of the do operator. We can make this if we have a causal model in mind. So on the left model, for example, we see that that Z is a common driver of both X and Y. So there's an influence which we are not interested in. So we want to block, or we want to account or extract the blue line only. So we have to block the influence of Z. And this means controlling for Z. And so in this case, doing X is the same as the observational condition probability given X and Z, because this means that we also accounted for Z. In the linear case, it's as easy as just including Z in the linear regression model. And in this case, we can then interpret the regression coefficient of X, A, as the causal effect of X on Y, because we control for Z. If we would only use linear regression of X on Y, again, this would be biased by this causal, by this common driver Z, which is a confounding factor. So again, this maybe was a bit abstract. Again, I give some more concrete examples with actual data and actually examples from climate science, which are probably easier to relate to. But there are 2 points I want to make. So first of all, it's really about expressing hypothesis or knowledge or assumptions using causal networks. And again, causal networks are really just these little diagrams at its basic, in its essence. And the second thing is that then we can really draw these causal conclusions. So we interpret conditional probabilities as causal effects. But this, of course, means that the results or this interpretation is conditional on the causal network. So it's really a way to present conditional results based on some assumptions. But it's about really making these assumptions explicit to really bring in this causal reasoning, or to bring in our causal knowledge in the statistical analysis. But okay, now let's move to these concrete examples from climate science I talked about to give you more intuition of how this works, and actually to show you that it's really easy and that actually usually involves really small changes to scientific practice. And before I start, I just want to talk about the term teleconnection, which is what I'm mostly working on and which maybe is not familiar to everyone right away. So, so a teleconnection, what's usually, or the most prominent one is El Nino, or is the effect of El Nino southern oscillation, which it has on different regions. So for example, we have enhanced sea surface temperatures in the tropical Pacific, and this is known to trigger a wave train into the mid-latitudes, where it can also interfere with with circulation, or where it interferes with circulation there, and for example can lead to heavy rainfall in the southern US, or heat waves in Western Canada. So again has an effect on temperatures, on precipitation in North America, but also in other regions. This is well known and well studied, but the problem is also just shown an example. So we're often really interested in quantifying the contribution of teleconnections to really improve our understanding of regional weather and climate variability. And this is related to several tasks, including making attribution statements of regional extreme events.
Marlene, we just have a question about nonlinear
sure. case.
I don't know if you want to respond quickly, or maybe you'll probably deal with it later, will you?
Yeah, I can just quickly say, so I mentioned the linear case, or the meaning that if you assume that there's a linear relationship, then we would of course use linear regression to quantify this relationship. But the approach is fully non-parametric. So in this talk, I will stick to linear regressions just because it's easier to visualize and to explain. But actually, on the lecture on Thursday, I have also an example with nonlinear to quantify nonlinear relationships. But again, in the essence, it's about understanding which variables to control for, and whether then it's a linear or nonlinear relationship. This is then another assumption, let's say. But yeah, I think the nonlinearity is better explained on Thursday. I hope this is sufficient for now. Okay, so yeah, so teleconnections, it's well known that we have to quantify them, that we have to understand their contribution to regional climate and weather. The problem is that they're really, well, it's not only ENSO, but it's really also sea surface temperatures in different regions, or soil moisture or snow cover, which can affect weather and climate around the globe. So it's hard to disentangle the different contributions. So extracting this information from data is usually quite difficult. Again, to show kind of this disconnect between physics and statistics, I like to show this this definition of a teleconnection by the American Meteorological Society, which they define a teleconnection as a significant correlation in widely separated points. So using statistical concept, because such correlations suggest that information is propagating. So I think this nicely shows this disconnect between the physical or the mechanistic understanding of a teleconnection, which is from cause and effect. So sea surface temperature cause or contribute to causing a heat wave, but we usually just use correlations or linear regression to quantify the contributions of teleconnections. So it's about moving beyond that. And this motivated a paper of ours where actually most of the examples I will present in these lectures are based on. So in this paper, we address exactly this question: how to formally include causal, or that is physical reasoning, in the statistic analysis of teleconnections. So in the following, I will stick to teleconnections when talking about assessing causal relationships in the climate system. But again, it's not bound to study teleconnections. But again, this is the field where I'm most familiar with. Okay, to start to give you some intuition, this is a very simple example, again, that of a common driver or a confounding factor, if you wish. In this case, I'm always using observation data or reanalysis data, in this case using NSUB dataset. And what you can use using this data, which covers, I think, 60, 70 or 70 years, you can see that precipitation in Denmark and in the Mediterranean in summer, they are significantly correlated. So there's a correlation of minus 0.25. Well, if we ask, does this reflect a causal relationship? Again, by bringing in our causal reasoning or physical reasoning, we would probably say no, because we know that precipitation, both regions, are affected by the position of the North Atlantic storm tracks, as, for example, expressed by the North Atlantic Oscillation Index, the NAO. So expressing this as a causal network gives you this diagram shown on the left, with the NAO being a common driver of both Denmark and Mediterranean precipitation, but would actually not assume that precipitation, these two regions, are somehow causally affecting each other. What we're of course interested in is quantifying the causal effects. So we are interested in giving numbers to these arrows. Assuming this kind of causal network is basically expressing what we're interested in, so that there are no other common drivers of any two variables included. So if we're interested in quantifying the contribution or the effect of the NAO on dynamic precipitation, and assuming again now that linearity is a valid assumption, we can use linear regression and quantify, using standardized linear regression in this case, quantify the effect as negative and giving it a regression coefficient of 0.55. Again, assuming there's no common driver of Denmark and the NAO, then we can actually interpret this regression coefficient as the causal effect, because no common driver is messing up, let's say, with this number. The similar way we can also quantify the contribution of the NAO in Mediterranean precipitation. Again, interpreting this or saying this is if this model or this causal network on the left is correct, then we can interpret this causally. What's important here is, or what to interpret our data now is that that the product of these two causal effects, it's actually the same as the correlation between Denmark and Mediterranean precipitation. So, and this follows from very simple algebra. If you decompose regression coefficients and correlations to covariances, you can, and I will also share references at the end of the lecture or in the next lecture. You can really see how really the causal effects explain the correlations. And of course, this makes sense, so that we know that if we have a correlation, it does not imply causation, but there's of course some cause involved, but just the cause can be indirect or it can be a common driver, like in this case. So the causal effects, they can explain the correlation we found, again, conditional on our network. In a similar way, we can also ask whether the data we have, if it's consistent with our causal model, with our causal network shown on the left. And we can do this by just thinking that, okay, if I blocked the influence of the NAO, so if I had some way to regress out or to remove the effect of the NAO on these two variables, would I still see a correlation or some association between the two? Because if it's really if this is the common driver and there's really no causal relationship between Denmark and Mediterranean precipitation, so there's no arrow between them or connecting these two, then there should not be any association left after regressing out its common driver. In the linear case, we can easily do this just using partial correlation. So we just correlate the residuals after regressing the two variables on the NAO. And in this case, if we do this, so if we compute the partial correlation, regressing out the effect of the NAO, we get a partial correlation coefficient, partial correlation close to 0. Basically meaning that really all the associations, all the information they shared was explained or introduced by the effect of the NAO. Again, this is a simple example, but I do like it, and I think, or I hope it shows well that really this causal knowledge, such as this in the simple form of this causal network, is really needed to interpret, on the one hand, these causal, but also these non-causal associations. So we can use this knowledge to quantify causal effects. At the same time, we can also use this and test this consistency with the data to actually make sense of spurious correlations, and we can really attribute them to causal effects or causal drivers. Okay, so this is another example. It's also a simple one. And it's related to ANSYS, so the El Niño Southern Oscillation, which I also showed in this on this schematic on the teleconnection slide. So this causal network here, this represents how ENSO affects the position of the jet stream in the North Pacific, and this affects precipitation in California, in this case in winter. And assume we're interested in quantifying the effect of ENSO on precipitation in California. So we are interested in asking, how strong the influence really is. What's often done is that if we have data of 3 variables available, we just put everything in a linear regression model. So assume this would look, our linear regression model would look like this. So in this case, we get so California is expressed as a function of ENSO and jet. But in this case, we get a very small regression coefficient of ENSO, suggesting that the contribution of ENSO to California precipitation is very small. And again, we have to be careful here. And in this case, we should not interpret this regression coefficient causally, in contrast to the previous slide in the NAO example, because what happened here is that by including the variable jet in the regression model, we blocked this causal or this assumed causal pathway from ENSO to jet, just as including NAO regressed out the effect of Denmark and Mediterranean precipitation, the partial correlation. In this case, we block the influence because we assume that the influence of ENSO is mediated by a jet. So its influence or its causal effect is already contained in the variable jet. So what's actually the correct way to do it? Given that there is no confound, or that we don't assume a confounding factor of ENSO and California precipitation, so it's basically these 2 variables, we can quantify the effect directly. So we don't have to include jet if we're interested in the contribution of ENSO in this case. And we get a regression coefficient of 0.34, so much higher than the 0.005 from before. Or alternatively, we can also quantify the different aspects of the pathway. So we could quantify the influence of ENSO on jet, getting an effect of 0.37, or we could quantify the influence of jet on California precipitation. And in this case, again, there's no confounding assumed, so we can just quantify directly using linear regression and not including any other variables. And we get a contribution of jet to California precipitation of 0.81. Again, all these are standardized regression coefficients. And then again, we can, since we know that the causal information is propagating us through this pathway, we can again see that the product of the 2, so along the pathway, is basically, or it's almost the same as quantifying the effect directly. So again, we can just quantify the effect of ENSO directly, or we can quantify the different aspects of this chain, which gives us the same result. So again, making sense of the data just based on this causal network, or based on our causal physical reasoning of how these different variables are related. So at this point, so we talked about on the one hand on this common driver and on this, so this was example 1, and on this mediating pathway, which was related to example 2. But these very 2 basic examples, they already show the importance of causal reasoning, because just from a statistical point of view, these 2 examples are really undistinguishable. So in both cases, we have 2 variables which are correlated. So in the first example, we have Denmark and Mediterranean precipitation being correlated. And in the second example, we have ENSO and California precipitation being correlated. But once we condition, or once we regress out the effect of the common driver, of the third variable Z, the 2 variables become independent. So in the first example, we conditioned on the NAO and found that there was no association left between Denmark and Mediterranean precipitation. In the second example, when we included jet in the regression, so once we controlled for the variable jet, actually we found that there was no correlation left between ENSO and California precipitation, or just very little one. So in both cases, we have 2 correlated variables which are independent after conditioning on the third variable. So, but really the interpretation is very different, and this really shows that really cause interpretation really enters through our physical knowledge. In the first example, we accounted for we wanted to account for the NAO to show that they're independent. In the second one, we assumed it to be a mediator, so we didn't want to control for it in order to estimate the effect of ENSO and California precipitation. Well, to combine, let's say, these 2 aspects, here's a third example, which is about quantifying indirect and direct effects. Again, it's we have ENSO, but this time in the southern hemisphere, so it's effect of the southern hemisphere. So we're interested in the effect of ENSO on the position of the southern hemisphere jet stream in OND, October, November, December. We know that there's a direct effect of ENSO on the jet, on the position of the jet, but there's also so-called indirect pathway from ENSO to the SPV, which stands for the stratospheric polar vortex. So ENSO affects the stratosphere or the circulation in the stratosphere, which also has an effect on the position of the jet stream. If we're interested in quantifying the total effect of ENSO on jet, we don't care about, let's say, all the different mediating pathways. We can just quantify directly and here get an effect of 0.14. But often we are really interested in to say, for example, what is the dominant pathway, or which pathway is more important. So we can also do this, but again, we have to think about what are the confounding factors when quantifying the different links. So for example, assume we're interested in quantifying this direct tropospheric pathway. So we don't want to, we want to only quantify the effect from ENSO directly to jet stream. In this case, we want to block this mediating pathway. And again, blocking this mediating pathway, we just have to, in the linear case, we just have to include the mediating variable. So in this case, when I want to quantify the direct effect of ENSO on jet, I also include this mediator SPV of the indirect pathway. And this way I can interpret this regression coefficient of ENSO as the causal effect of, or the direct effect of ENSO on jet. Again, conditional on this causal network, assuming there are no other factors which we forgot to involve, for instance. Might also be interested then in quantifying this indirect, this stratospheric pathway. And this consists of two steps. So first, I want to I can quantify the contribution of ENSO on SPV, on the polar vortex. Based on my model, there is no confounding factor of these two, so there is no common driver of ENSO on the polar vortex. So I can just quantify the contribution directly and interpret this causally, conditional on my causal network, and get a regression coefficient of 0.26. Then I can also quantify the contribution of the polar vortex on jet. In this case now, ENSO is a common driver of the two, so it's a confounding factor. So to extract the causal information from the polar vortex only, I also have to include ENSO in my regression coefficient, my regression model, sorry. And I get a regression coefficient of 0.39. Then the product of them is 0.1, which is then the strength of this indirect stratospheric pathway. Again, we can do the math and just say that the tropospheric and the stratospheric pathway, so the direct and the indirect pathway, is just the sum of the two. So there are two ways how ENSO affects jet. And you see this is the sum of them is 0.14, which is the same as estimating the effect directly. So we basically decompose the total effect in this indirect and this direct effect. And well, as if we show an example in this case, the numbers really add up nicely while supporting also this causal network. Okay, so I have a few 15 minutes left, and I will try to kind of summarize what I talked about so far, kind of bring the different pieces together. At the same time, I will also give a very short outlook for the next lecture, to basically say what we didn't cover yet, or to, let's say, what is missing and what you might also have maybe questions on. Okay, so basically there are different basic causal structures, and we have three variables, and they have different implications for data. So the first example was that we have that Z is a common driver of X and Y. So this was the same as the example with the NAO. So you see the arrows point out of the variable Z. Or Z can be a mediator of X and Y. In this case, we have this chain, so X causes Z causes Y. And if these, in both these cases, the implication for data, so if this is the causal structure of our three variables, the implication for the data is that X and Y are correlated, but they should be uncorrelated after conditioning on Z. Again, it depends on our question and on the causal relationship, whether we then condition on Z or not. In the case of a common driver, we usually regress out its effect, control for it to regress out its effect, whether if we're interested in the effect of X on Y in the case of a mediator, then including Z in the regression actually regresses out the effect we're interested in, as shown in the second example. There's a third option actually where Z can also be a common effect of X and Y. So in this case, the arrows from X and Y, they point towards Z. I didn't cover this yet. This will actually be covered on Thursday, but I just want to mention here that the implication for the data is that X and Y are actually independent of each other, so they're uncorrelated. But once we condition on Z, so actually we introduce a correlation of X and Y. So we have to be careful here too. And again, I will give an example of the third case on Thursday. So it's really these, let's say, three different basic causal structures which have implication. But of course, in science, we don't only have just variables which are relevant, but really this can be a long list of things which are relevant to a scientific question. So just to bring up this slide again from the beginning, we usually start by the first step is always to express this causal our causal knowledge as a causal network. And again, and this causal network then usually consists of different combinations of common drivers, mediators, or common effects. When we then have collected the data, it's really about controlling for the confounding factors to extract this causal effect of interest. And again, this really depends. So the confounding factor depends on the interest of the interest. So we usually should not just control for everything, but we should really just pick on the things which mess up the causal effect we're interested in. Again, it's about the idea of a causal effect is that it's the same of doing interventions, but we don't do it with the data, but we just want to express the SPU operator or the effect of an intervention using conditional probabilities. And this way is when we can do this after controlling for all the confounding factors. In the linear case, this is pretty easy. And we can just include Z, the common driver or the confounding factor Z, in the linear regression model. And the examples I showed you today, again, we just had these three variables. So we basically made this very intuitively and to see whether there's a common driver or not. Of course, in scientific practice, we have more variables and things get maybe a bit more messy or complicated. And so we talk on this on Thursday, how we can actually basically providing an algorithm how to identify the confounding factors and how to deal with this in the presence of more than just three variables. So again, the examples from today were more to give you some intuition where we can really see what is a common driver, what is a mediator, and how this affects the data. So kind of the take home message is really from this first lecture is first of all, well, correlation does not imply causation, but of course correlations are also the result of causal relationships. So I guess I showed with the toy example, but also from this example from climate science, that we really need causal knowledge about the mechanism which generated the data, which is correlated, or the data we see, to make sense of the data, to, on the one hand, to interpret correlations and to say whether they are causal or not, but also to extract the causal effect of interest, which is somehow hidden in the correlation. So it's really about extracting the cause effects from the data by using the causal reasoning. And then causal inference is really this mathematical discipline which gives you the formal rules how to achieve this, so how to extract when it's possible, and how to extract the cause effect from the data. What really has been shown, which is really beneficial, is really to express this causal knowledge or the causal hypothesis using causal networks. So really just draw diagrams of how one thinks how the different variables are related. And then the key point is really to control for the confounding factors in order to extract a causal effect from data. Because again, the causal effects or the effects of interventions are they're present in the data, but again they are biased or they by these confounding factors, which is also some interventions would happen in the climate system. The very key point is really that scientific data analysis, so the data analysis we do as climate scientists, this really requires causal reasoning, and causal inference give you the rules or the framework to do this in a formal way. So yeah, in the bigger picture, I think it's really about bridging physics and statistics. So we have approaches from two worlds, as I mentioned at the beginning. So we have our physics-based methods, numerical climate model simulations, and we have our data-driven methods, which nowadays also get more and more popular with the rise of machine learning and climate science. A causal framework, in my opinion, is really a way to connect the two and to bridge the two. It's not a method itself, it's really a framework to formalize or to force you to be explicit about physical assumptions, and then combine them with your data analysis in the best possible way. For example, to make sense of correlations and to interpret correlations in a causal way. So these are really the main points for this lecture. Again, as an outlook, tomorrow there will be practicals, and I think, or Elena told, so there will be practicals also going through these examples, also different examples using Python. And I believe the instructions have already been sent around, or if not, they will be sent around. So again, it will be done with Python, and you will have to you can, for example, do it with Google Colab. But again, there have been email instructions which you can just read basic steps you might prepare, and otherwise Elena will assist you in this. I believe she's also the call today. Yeah. And then yeah, perfect. Did I miss mentioning something for tomorrow?
No, it's okay. You said everything. The email has been circulated yesterday evening, so
perfect.
It'll be
okay.
fine.
So then it should be clear. And then again for the next lecture, to give you a teaser, so I will talk about the effect of conditioning on a common effect. So kind of what happens in the case of this third example, of this third data structure. So if X and Y are a cause of the third variable Z. Then I will also give a bit more formal way of how to control for the correct pathways to isolate the cause effect of interest. So moving a bit beyond intuition, how to deal with the three variables, which again, you might just have done intuitively, where you don't really need causal inference. But I will show you one example where I think it's basically impossible without drawing a causal network first. And then I will also give an example of how to quantify nonlinear causal relationships. Again, today I just used linear regression only, assuming that all the relationships were linear. And if time permits, but I think so, I will also briefly talk about actually causal discovery, so which is about learning causal structure, or basically learning the causal network from the data. So where one starts with time series and learns the causal network rather than the other way around. So that's it for today, but I guess there are some questions.
We have two.
Thank you for,
Thanks, Marlene. We have two. So Loritz, and you can turn on your camera as well and ask your question, and then Sahil after that.
Yes, thank you very much. It was a question about the NAO and Denmark Mediterranean network. So when you say you condition on the NAO, do you then assume a specific value for the NAO index to calculate the new correlation?
Sorry, I didn't explain this well, so thanks for asking. I expressed this as correlation conditional on NAO. So this is partial correlation. And you can actually, to give you an intuition what this is, you can first think of these two regression models. So in this case, we basically quantify how much the NAO explains of, on the one hand, Denmark precipitation and the Mediterranean, right? So you could, if you think of a linear regression model of these two, you would have the residuals, which is kind of the unexplained part of these two variables. So what you can do is you just take the residuals. So basically you have Denmark minus this part and Mediterranean minus this part. And then you can see, you can check whether the residuals are still correlated, whether there's some structure left, basically. Mm-hmm. And in this case, we find the residuals. So after removing the effect of the NAO, which is quantified to be this, and after removing the effect of the NAO, we basically find no more correlation of these two variables. So partial correlation is just correlation of the residuals after doing the regression with this other variable. I hope this.
Yeah, that makes really good sense. Thank you. Thank you.
But you could add that in the nonlinear case, you would then choose a value or like a tercile or something like that, right? Yeah.
Yeah, true. And again, will be covered tomorrow on Thursday.
Okay, and then Sahil, turn the camera on too.
Yes. Hi, Marlene. My question is, can machine learning methods be directly used for causality?
I like the question. So, well, maybe this is definitely a bigger debate. So the answer is, well, I guess yes and no. So maybe if you look at this causal ladder, or the ladder of causality, you actually see robots, or maybe that's kind of representing machine learning. You see it at the lowest level, so it's really just as the seeing level. With Pearl, who actually, well, one of the pioneers of machine learning, is also one of its biggest critics, if you want. And she really says that all the machine learning methods, it's really just curve fitting, and we're basically very sophisticated way of computing association. Or I don't know if it was him or someone else. It's kind of statistics on steroids. Well, whether you agree with this or not, I think it's definitely clear that most of the machine learning methods, well, are based on fitting association. So they're not particularly well suited usually to extrapolate. Again, in climate science, this is a problem because we have climate change. So we can fit associations in our data now, but when we want to extrapolate and make predictions of the future, this might be a problem. So the answer is no. So machine learning is usually at the association level, but there's really a huge field on causal machine learning. So on the one hand, for example, machine learning can be used to quantify causal effects, or nonlinear causal effects. So for example, if you assume a nonlinear relationship, linear regression is too limited, then machine learning methods can be powerful to quantify causal effects. Again, but this still requires some causal model in the first place. And then, of course, there are also machine learning methods which deal more with this learning causal structure problem. They also require some more assumptions. But again, it is, on the one hand, machine learning is really also about association, just a bit more, or just better than just purely correlation, because it can really fit complex dependencies. But combining causal reasoning with machine learning is really, I think, a huge field, and will really probably change the field.
Yeah. Okay. Thanks very much. We should take a 5-minute break now, and we'll start with Sebastian at 5 past the hour. Thanks, Marlene.
Thanks, and see you on Thursday.